When we're dealing with first-order differential equations, we'll come across a form sometimes that looks very much like a linear form, but with an extra term on one side. So here you can see our Bernoulli form is dy dx plus some function of x times y equals not just g of x, some idea function of x, but actually g of x times y to a power. So if you look at this portion of the equation all the way up to g of x, it looks like the linear form. We have this additional multiplication by y to some power on the right-hand side, giving us what we call this Bernoulli form. So you can see some examples down here. If we look at this, so we basically have a linear equation, but the right-hand side is multiplied by y to the 5, so n equals 5 here. Over here we have basically the same thing, except on the right-hand side we have 1 over y cubed. In other words, here n is equal to -3, etc. Right? So we have our dy dx plus this is our function of x times y. Our e to the x is our g of x, and then y squared, obviously, n is equal to 2 here, etc. So when we look at solving equations that are in the Bernoulli form, the idea is, since it's very similar to a linear equation, we're going to just simply do some operations and a substitution that will allow us to get it into a linear form in terms of a new variable. Okay, so our goal here is to change it into a linear form and then solve the new differential equation we get that's in linear form using the methods for linear. Okay, so here our example, we have dy dx plus y equals x times y to the 4th. So what we're going to simply do is divide out that y to the n. Okay, so our first step, we're going to divide everything by our y to the n that's on the right-hand side here. So we'll divide everything by y to the 4. Doing that will leave us, I'm going to go ahead and write this as y to the -4 dy dx plus, and then this becomes y to the -3 equals x. Once we divide by y to the n, the next step will be to make a substitution. And what we'll want to do is we'll want to choose the power of y we get here in our non-dy dx term. So step 2, we're going to substitute. And I'm just going to use the variable v, so I'll let v equal that y to the -3. And the reason we're choosing that is because we're always going to get one less power of y over here by dy dx. So when I do my substitution of y equals v to the -3, then when we find the derivative, in other words dv dx equals -3, and then the power goes down by 1, y to the -4 dy dx. Okay, so now what we have here is just simply a multiple of what we needed also to get rid of the remaining y's. So now if I want directly a substitution for this y to the -4 dy dx, I simply need to take this expression here and divide both sides by -3. So we would get -1/3 dv dx is equal to our y to the -4 dy dx. Okay, so we take our original substitution, v equals y to the -3, this expression that we got for the first term, we plug both of those in over here, and we'll get -1/3 dv dx plus y to the -3 was v equal to x. And now this is linear, and we just want to do a little adjusting for that -1/3. So we'll go ahead and take the entire equation here and we'll multiply by -3 to clean up that first term. So that gives us dv dx minus 3v equal to negative 3x. And now this is exactly in linear form, the way we usually think of it. And so here f of x is equal to negative 3, and g of x is equal to negative 3x, if you're very familiar with linear. And so the next step here would then be to most likely find an integrating factor. So our integrating factor will be equal to e to the integral of f of x, which is negative 3. So that will give us the integrating factor is e to the minus 3x. So we take the entire equation here and we multiply by our integrating factor. So that gives us e to the minus 3x dv dx minus 3 e to the minus 3x v equals negative 3x e to the minus 3x. So we're very much in linear land now. And if you know linear equations well, then you should be on your way here. So what we want to do is then integrate both sides dx, and then we will be near a solution. So we go ahead and integrate. Remember, this side over here is always going to be a product rule for the integrating factor times our variable v there. Equals, and now to integrate this side we would need to do it by parts. Maybe I'll go ahead and look at doing the tabular method here. So we'll go ahead and say we'll choose u to be negative 3x, and we'll choose our dv to be e to the minus 3x dx. And we'll continually differentiate u, so that will give us negative 3. And then when we differentiate again, it'll give us 0. If we integrate e to the minus 3x, that'll give us negative 1/3 e to the minus 3x. And if we integrate again, that will give us 1/9 e to the minus 3x. And our signs will change according to the by parts rule. Alright, and so then if we connect our diagonals here, we should end up with what we need on the right hand side. So we get negative 3 and negative 1/3 will reduce, giving us x e to the minus 3x for the first term. And then we have a negative 3 and a 9th, and then we have another negative, so that'll give us plus 1/3 e to the negative 3x plus a constant. And then we can go ahead and obviously if we divide out this e to the minus 3x on both sides, that'll leave us v by itself. So divide both sides by e to the minus 3x, that will be v equals x plus 1/3 plus c, it would be divided by e to the minus 3x, so that would be like times e to the regular positive 3x there. And then just simply remember here that we let v equal to, our original substitution was y to the minus 3. So what we could go ahead and say to write back in terms of our original variable y, we could say that 1 over y cubed is equal to x plus 1/3 plus c e to the 3x. And then at that point, it's up to us if we want to do any more manipulation with that, or if we want to leave it like it is. Quick summary of things in Bernoulli form that are first order. So we have the form here, and the first thing we do is divide by that y to the n term. That'll give us a new form. We then make the substitution for the power of y here, and then when we differentiate that substitution, we should get an expression for this lead term here. Once we do that, we have a new equation that is linear in the terms of our new variable that we chose for our substitution. We then solve it using the linear methods, usually by using an integrating factor, and then once we solve for v at the end, we can go back and substitute back in for y.